Now this is known as the fluid equation. This equation can be used to determine the pressure of different components of the universe, or conversely, how ρ changes in time. For that, we need an equation of state. We can write that the equation of state is, by definition, equal to W, little w, this is not omega, this is W, times the internal energy density. Substituting the mass energy equivalency, we have it equal to W times rho c squared, where W is a factor to be determined for each component. We already saw that for dust, that means either matter or dark matter, there is no pressure. So for dust, that means matter or dark matter, including dark matter, you have W is equal to 0. Now, if you plug W equal to 0 in the fluid equation, you're canceling the right-hand side. So for matter, the fluid equation becomes d dt, the time derivative of the density times the cube of the scale factor is equal to 0. So we get that for matter, cube of the scale factor times the density is constant. And that is the relationship that we have been using. You have a geometrical dilution of matter density as the universe expands. Now, in general, for the pressure given by the equation of state, with W not equal to 0, the fluid equation is, right now, this equation is a bit cumbersome because you have time derivatives on both sides. We can try to find a chain rule so that we have a single time derivative instead of two. Let's go back and then write the fluid equation with the general equation of state with W not equal 0. And let's try to find the chain rule that leads to a single time derivative. Well, first, let's sum the right-hand side on both sides and expand this derivative of a cubed. So that is 3a squared times the derivative of a. That equation then becomes, and now we can substitute rho times a cubed by alpha. And then this equation becomes the time derivative of this alpha, multiply and divide the second term by a, and then you have 3 times w of alpha over a times dA dt. This equation is equal to 0. So if you have d alpha dt in one term and alpha on the other one, this looks like a product rule, a product derivative. So let's use the product rule here to simplify this equation. Let's use a multiplicative factor. Multiply this equation by beta, a multiplicative factor. This becomes beta times d alpha dt plus 3w beta alpha over a times dA dt is equal to 0. And now we equate this to the product rule, that the derivative of alpha beta is equal to beta times the derivative of alpha plus alpha times the derivative of beta. So the first term is, of course, identical. That's beta times the derivative of alpha. The second term is correct if we identify these two terms. That means that the derivative of beta must be 3w over a times beta times dA dt. So solve this for beta. This equation then gives you the log of beta is equal to 3 times w times the log of a. So you find beta is equal to the scale factor to the power of 3w. So we succeeded in writing the fluid equation in terms of a product rule, provided that beta is equal to a to the power of 3w. That means that the time derivative of alpha beta is equal to 0. And given what we found for beta, and again substituting alpha, this equation then means that the time derivative of the density times a to the power of 3, 1 plus w is equal to 0. So this quantity inside the derivative is conserved. Now this equation can be used for any fluid that we can write the equation of state in terms of the pressure is equal to w times rho c squared. And given that the scale factor present is equal to 1, then any such substance will follow this equation, meaning that a to the power of 3, 1 plus w times rho is equal to rho naught, which is constant.